Remember when we were talking about diodes? We said a diode is forward biased, a diode is reverse biased. Okay? So we use the word biasing a lot in electronics. And basically what biasing means is applying voltage or current to a circuit. That's all it means. You want to activate that circuit, give it some voltage, give it some current, and it turns on. And it may be somewhere fully open, fully closed, or in between, but that's what biasing means. So in a transistor circuit, how do I bias the circuit? By giving it a little bit of base current, right? Which causes it to turn on. So that's called biasing. So let's read the first note in the DC biasing circuit handout, page 1. When a transistor is used as an amplifier circuit, a small AC signal is amplified, and before you can use a transistor as an amplifier circuit, it has to be properly biased. What does properly biased mean? Find a proper location of its Q point. That's what proper biasing means. So note 2 says, biasing a transistor circuit means designing it for the proper value of the DC, VCE and IC, and setting a proper operating point on the DC load line. So there's my load line. Finding a Q point on it is called properly biasing. So there are many biasing circuits. There is a circuit called base biasing, which is what we're going to talk about. There's also voltage divider biasing, emitter biasing, collector feedback biasing, emitter feedback biasing. What does this mean? You take our basic circuit that we did in the previous notes and we tweak it. Let's change the voltage a little bit here. Let's connect it a little bit different. And that's what happens. And the whole point is to come up with different amplifier circuit designs. That's what the different biasing circuits are. So the base biasing is taking my regular circuit that I looked in notes 10 and combining VBB and VCC into one. That's what base bias, DC base biasing is. So, base biasing. If I combine VBB and VCC into one, what will the circuit look like? It will look something like this. Watch. This is VCC. I'm taking my VBB and merging it into VCC. Okay? So there's my VCC. Off of VCC, I'm going to have RB that's going to provide current IB. Okay? And off of VCC, I have RC that's providing current IC. And the two are going to become IP. Okay, so there's my circuit. So what I did was I did away with VBB and I merged VBB into VCC. I still need a voltage to provide to develop the base current, which is going to turn the transistor on, which will then cause IC to flow, which will cause a voltage VCE to appear in the circuit. So it's everything the same as what we did earlier, but everywhere that I used a VBB, I now use what? VCC. Because VBB and VCC are one and the same in this circuit. Okay? So this is the same circuit that you see on page 1. It's drawn a little different, but it's the same circuit. IB, IC, VCE, and one source voltage called VCC. So now what I'm going to do is take you to page 6. Go to page 6. On page 6, I've got that circuit, and I'm going to analyze this circuit, just like I did the circuit in notes 10. VCC, one source, 15 volts. RB, 500K. RC, 1.5K. HFE, 150. Draw the DC load line, calculate the Q point, the operating point of this circuit. Okay? So what you will realize after we do this 3 or 4 times is that it's the same thing over and over and over. You are going to draw the load line, so let's draw the load line. VCE on the x-axis, IC on the y-axis. 0 in the middle. Draw a line. This point, cut off. Open. This point, saturation. Closed. First thing I do is identify cutoff and saturation. Cutoff, totally open. If the transistor acts like an open switch, what is the voltage from VCE from collector to emitter? How much? 15 volts. Write down 15 right here. Saturation. IC sat. That's when the transistor acts like a closed switch. If it's closed, okay, that voltage, resistor, and that's it. So VCC over RC. 15 over how much? 1.5K. How much is that? 10 milliamps. Where do I show the 10 milliamps? At the saturation. That's when the transistor acts like a closed switch. Now, I find the Q point.